which is kind of a little bit of a course overview. So the idea here at the beginning, none of the stuff we're gonna talk about initially are things that I would consider like to test on. But I want to just kind of talk about a little bit about where we're going, especially in the beginning part of this course. Because it's, like this is a difficult course, and it's kind of wrapping two separate branches of mathematics together. We're going to take a lot of aspects of geometry and a lot of aspects of algebra, kind of cram them together. And there's a lot of nuance, and it can get a little bit overwhelming. But I think if you have a clear understanding of like what it is we're trying to do and what it is we're trying to accomplish, especially early on, I think it makes it a little bit easier to understand like, okay, wait, what are we doing now? Why is this different than what we did before? And like, what are we hoping to accomplish? I think kind of helps really kind of direct what it is that we're doing. So that's kind of where we're going to start here today, is just a little bit of big picture course overview. Okay? So the course title, or the focus for first semester, is this subject, trigonometry. When you look at the word trigonometry, what is the prefix or root word that you see there? Yeah, tri or triangle, right? And you guys can just yell it out. Like we don't have to raise hands. We're just kind of trying to be a little informal right now. And the triangle is kind of the foundational element for trigonometry. It's kind of the way or where this branch of mathematics is kind of begins. If you guys think back to geometry and you think back to triangles, what are some things you remember about triangles from geometry? Yes, sir.
They always form a total of 180 angles.
Great. So, yeah. Excellent. What else do we remember? Go ahead.
The normal right angles, it's usually 45, 90 degree measurement. Special, I think it's
yeah, 30, 60, 90, and 45, 45, 90 are the two special right triangles. Yeah. Good. What else do you guys remember? We're just kind of making a little bit of a list right now. Yes, Lexi.
There's three types. Isosceles, equilateral, and scale.
Okay. You said isosceles, equilateral, and scalene. I apologize in advance here about my penmanship. This is what my penmanship looks like. If you can't read anything, like, totally fine to be like, what does that say? I don't blame you at all. Yes.
There's also acute obtuse, right?
Okay. So this is based on sides, and this one is based on angles, right? So acute, no angles bigger than 90. Obtuse, you have at least one, well, only one angle bigger than 90. Right, you have one angle exactly 90. Isosceles, you have two sides, or at least two sides that are congruent. Equilateral, you have three sides that are congruent. And scalene, you have no sides that are congruent. Yes, sir? Sides. Right. Sides. Because that's what you're classifying by, is side length. Maybe I should write length there. Okay, that's good. What else? there's still two big ideas here that involve triangles that I'm hoping for. Elvis?
Triangle on 3 sides.
Okay.
SOHCAHTOA.
It's 3 sides. SOHCAHTOA, good. That's one of the 2 that I was hoping to see. And remember, SOHCAHTOA is just an acronym that describes how we define the function sine, cosine, and tangent, right? So if you remember, the way we define these things was if we had a right triangle and you specify one of the acute angles in the right triangle, say we'll call this one theta, we can describe the ratio of side lengths. Typically, we name those side lengths relative to the acute angle that we're focusing on as opposite, adjacent, and hypotenuse, where hypotenuse is obviously the longest side of the triangle. Adjacent is the other arm of the angle formed by theta, and then opposite is the side that's opposite, that isn't one of the arms of that angle theta. So for example, the SOH tell us that sine is equal to the ratio of the opposite side and the hypotenuse. Right? And then the ka, that's saying that cosine is adjacent over hypotenuse. And the toa is that tangent theta is opposite over adjacent. You guys kind of remember this? Again, everything we're talking about right now, I don't expect mastery of, right? Like this is just like, should be, oh yeah, that looks familiar, is good enough, right? I'm not expecting like, oh, I don't remember that at all. If you're somewhere ahead of, I don't remember that at all, we're good. Again, we'll go through and do all this stuff carefully, but a lot of these ideas, the foundational stuff, we've seen a little bit in geometry. So here's a tough question for you. What geometric principle is behind sine, cosine, and tangent? Like what's working in the background that allows this relationship to be true? And you know the answer to this. Lexi? It's not the Pythagorean theorem. What's up? Yeah, so there's a geometric principle at play that allows like these relationships to be true. That if you have a right triangle with angle theta, its sine value is always going to be equal to this number, regardless of the size of that triangle. So, for example, what we're saying is that, let me draw a picture, it'll maybe be a little bit clear, or more clear. So you have two triangles that both are right triangles and both have an acute angle theta in them. What we're saying is that that sine of theta in the one triangle needs to be the same as sine of theta in the other triangle. Right? Even though the side lengths are different length, the ratio of the side lengths need to be the same. What's that geometric principle that dictates this? Yes, Sergio?
Just the right angle.
It's not only the right angle. There's a specific geometric similarity. Yes. These two triangles are similar. So similar triangles, and let's start here with how do we know they're similar? Yes, sir.
Same shape.
It's that we know that all three angles.
I forget what the specific word is, but the size of one is just like half of the other. The size of one is double the other.
Proportional is the word that you're looking for. Yeah. So there are a bunch of angle similarity theorems like angle-angle that says that, hey, if two interior angles of a triangle are congruent, then the two triangles have to be similar. Because what similarity is really saying is that all the angles are congruent, and then the corresponding side lengths are proportional. That's the definition for similarity. So like side angle side is a similarity theorem as well as a congruence theorem. Or like angle side angle is a similarity theorem and a congruence theorem. But what this means is that this ratio of A over B needs to be the same as the ratio of C over D if they're similar triangles. And if we're talking about a right triangle that has also an interior angle theta or acute angle theta in it, has to be similar, right? Because the third angle has to be the same because of the triangle sum theorem. So that's what allows us to create this function sine that says, okay, well, I know that all right triangles with an interior angle of 56, the ratio of the side lengths are going to be this. Doesn't matter what the size of the triangle is. Could be gigantically little bit tiny. The ratio of opposite over hypotenuse is going to be the same if it's a right triangle with this other interior angle. Always. Yeah. Of course. Yeah, no problem. So we're starting off with our definition of sine, cosine, and tangent tied to these right triangles. Everybody's okay with that? Now, if you were in the honors geometry course, you saw that, okay, well, there's a way we can deal with sine, cosine, and tangent for, okay, well, hold on. Let me do one more thing. So this angle theta, the way we've defined it right now, has to be acute, right? Because we know we can't have a right triangle with another angle that's 90 degrees or bigger in it because you can't have a triangle. Everybody's good with that? Now, in your geometry course, you did a little bit more and at least mentioned a way to take sine, cosine of angles that are obtuse, right? That are between 90 and 180. Does anybody remember that way to do that? In your honors course, if you took the honors course, you would have talked about this as a way to do sine or cosine for angles that are obtuse between 90 and 180. I'm just looking for the name. Would be enough. And I'll say it and you'll be like, oh yeah. Okay. So there was the law of sines and the law of cosines. And we're not going to worry about those specific formulas right now, other than to mention like that we could use those to deal with situations where you had angles between 90 and 180. Right? So this was a way to use sine and cosine in non-right triangles, but it's still triangle based. Now, in geometry, when we talk about an angle, we're always talking about this measure, right? We'd never be talking about that measure. Everybody agree with that? But there's a lot of real life situations where maybe the green measurement would be a valuable way of describing this angle. Can anybody think of a real life situation where that might be the case? I wouldn't expect anybody to answer necessarily, but Drake?
shape or size in which a roof was made.
Okay, I think you could probably get away with that without doing that. Lexi?
I suppose in architecture, when you're looking at doors and the way they swing, it's determined,
I think you can still get away with just one or just the one way, because you can, because here you could use the other side, but I don't think you'd have to. Let me describe a situation which being able to use the other one becomes really potentially quite useful. Yes?
Oh, which of the two did you say we would use the outer one?
Yeah, the green. Yeah. So imagine you're navigating. So like you're flying a plane or piloting a ship, or even like, walking on foot. All of a sudden, if you're talking about navigating this fashion, like left and right turn is kind of meaningless, right? Because everything's not laid out on a grid. You're not walking on streets where there's a natural grid in place. Everybody agree with that? So if I want to go from here to here, I'm going to turn, like this much. And then if I want to go back to where I started, I would either be doing this, where now I'm flipping the orientation, or I would be describing this turn. Now, from a practical sense, if you're trying to communicate what you're doing to someone, or how you go from one place to another, do you want to be constantly having to worry about when are we flipping the orientation, about whether we're talking about going to the right or going to the left? That sounds terrible, right? Like having to consistently worry about that. You'd want to describe your navigation always going, okay, we're going either to the right or to the left, but we're just going to pick a direction and call that the way that we're always describing our angle, right? That's a situation where the other side of a geometric figure becomes a valuable angle measurement, right? Does that feel, just in terms of practically communicating that information, that becomes really valuable to have that be a valid angle measurement? So that's our first extension we really want to do, is we want to go ahead and say, okay, we can describe sine, cosine, and tangent for acute angles using just right triangles, like we did in geometry. Pretty easy. What if I want to now describe sine, cosine, and tangent for angles, and we can even do it for obtuse angles that are still tied to a triangle, right? Like we have for the law of sines and law of cosines. But what if I want to include like a 210 degree angle that can't be tied to a triangle, but would be a valid in this kind of situation, right? So that's the first extension, is we're going to take sine and cosine and tangent, take it outside of the right triangle, and design a way to apply it so we can deal with angles that are bigger than 180, but still smaller than 360, right? Because if I draw this, I can't have, like if you do something like this and like, right, you can get real close to 360, but you can't get to 360, right? Everybody agree with that? So that's the first extension we want to do. But now, imagine this situation. Again, a practical situation. Imagine you've designed a machine, and a part of that machine spins. So like if you're talking about an automobile, like the drive shaft of a car spins like this, right? Everybody's okay with that? You imagine underneath the car they have the piece that goes to the wheels and makes the wheels go from the engine. That's the drive shaft or whatever, I think. I'm not a mechanic. But it spins, right? And certainly something you might be interested in is, okay, in a second, how many times does that spin? Right? You're now talking about an angle that's rotating more than 360 degrees, right? If you have more than one rotation, you're talking about an angle that's 720 degrees or, 1,000 degrees or whatever, right? Everybody's okay with that? And in a car, when your car's in drive, the drive shaft spins one direction, but if you change your car to reverse, what's going to happen to that drive shaft? It's going to turn the opposite direction, right? Because the wheels have to spin the opposite way. So if one of them is moving the car forward and one of them is moving the car backwards, what is that kind of implying there? One of those angles should be positive, and one of those angles would be negative. So that's the next extension that we want to do, is we want to extend this system so that we can deal with sine and cosine for angles that are any size, whether they're really big positive or really small negatives. And that's going to be most of our first semester is going to be spent taking sine and cosine out of the right triangle and breaking the triangle part off of it and dealing with, okay, we can now do sine and cosine and tangent of any number you want. I can do it. Everybody okay with that idea? So that's the main focus here of first semester. The end of first semester and a lot of second semester, like the first half of second semester, is then going to be looking at other systems other than just like angles and sine, cosine, tangent that are kind of constructed using a similar system. So like we'll talk about vectors and polar coordinates and parametric coordinates and like three-dimensional lines and planes and things, and all of these kind of chunk in nicely to be kind of the same thing that we've done over and over again. Like it's still the same system, even though it's a completely different setting. We can construct the system around it the exact same way, and everything works basically the same way. So it's critically important in the beginning that we understand these relationships and like, okay, in this setting, I can look at this very narrow right triangle definition of sine, cosine, and tangent and get away with things. But as soon as I get this situation, now I need to use this other representation where, I can deal with angles that are between 0 and 360. And then like, but this situation, I need to use this other representation because now I have to deal with angles that are, bigger than 360 or less than 0. And that's kind of the main skill here in first semester that we really kind of need to get mastered. So we just kind of talked about it. We didn't talk at all about how to do these things and how we're going to make these extensions. But just I wanted to give you an idea of where we're going and what we're doing. Now, we're going to start even further back than this to start the year. So sine, cosine, and tangent are functions. So we're going to start way back like we did in the beginning of Algebra 2, talking about like what a function is and some properties of functions and like representations of functions and this and that. Then we'll get back to this where we left off in geometry and start building out these definitions of sine, cosine, and tangent. And that'll be really what first semester looks like. I'm going to stop